Hello, welcome to Genetic Algorithms, what they are, and how to build one. In this course, I will be explaining what a genetic algorithm is. I will walk through its benefits and its limitations, some possible use cases. I'll explain the elements of an implementation, the steps taken by an algorithm, and then I will walk you through an example implementation. So first off, what is a genetic algorithm? Well, it's an algorithm which simulates a population of organisms to attempt many different solutions to a presented problem. So this is a combinatorial algorithm. It tries out a multitude of different combinations of potential solutions and then returns you what it thinks is the best one. In order to represent different solutions, we utilize gene sequences. In nature, a gene is a combination of proteins, as displayed here, usually represented by the letters A, T, C, and G. With a genetic algorithm, the most common representation of a gene sequence is utilizing a combination of bits. Each bit represents a piece to the puzzle, 0 being off and 1 being on. There are other ways to simulate genes, as displayed here. It's a combination of letters and numbers, with each portion of the string representing weight, color, or position. There are many benefits to utilizing a genetic algorithm. They are able to attempt many different combinations very quickly. They can provide multiple optimal solutions. So this would be different combinations that achieve the same goal. And they require less information than some other machine learning algorithms. Take, for example, a neural network may require thousands of photos as examples in order to correctly classify an image, whereas a genetic algorithm simply needs to know what are the different items or pieces of this puzzle that I'm trying to solve, and how do I score my different combinations. However, genetic algorithms also have their drawbacks. Complex problems require expensive calculations, so this would be how the algorithm determines a score for a given combination. The best solution is the one that it found, not necessarily the best possible solution. So if you're looking for an extremely accurate algorithm, this wouldn't fit your needs. Some possible use cases for a genetic algorithm include finding the shortest route between two cities, automotive design. This would be trying out different combinations of materials and designs in order to achieve a certain level of aerodynamics, or encryption and code breaking. Let's say testing out many different combinations of a password. So what makes up a genetic algorithm? In general, there will be an individual. This is a specific combination. There is a population. This is a set of individuals. Generation. This is the current population being evaluated. A constraint. This would be like if you're loading a truck with product, you only have a certain amount of space available. A value to minimize or maximize. This would be if you're loading a truck and you're trying to maximize the amount of money you can make from your shipment. A fitness function. This is how you determine how well a certain combination performed. Recombination or reproduction, this is creating the next population of individuals. And mutation, this is a small chance that a bit will flip from 0 to 1 or 1 to 0. Let's walk through the steps that a genetic algorithm takes. So at the start, we define a constraint. Let's say we're loading a truck. Our constraint would be the space available. Define value to minimize or maximize. This would be we're trying to maximize the amount of profit that we can make from our shipment. We create an initial population. This is an assortment of randomly generated combinations to kickstart the process. We evaluate the fitness of our population. We select the parents to continue on and recombinate or reproduce in order to create our next generation. We mutate the children, so we provide the opportunity for a combination to alter after it's been reproduced. And then we check our termination condition. So if we reach a certain threshold, so say we're trying to reach at least $10,000 in profit with our shipment, or we hit our generation limit, so we want to run this for 100 generations and then see what the best solution is. So once we've reached that termination condition, whatever it is, we reveal what our solution is that our genetic algorithm found. If we have not reached that termination condition, then we start the process over again. We go back to evaluating the fitness of the current population, select parents to continue, recombinate, mutate, and then we check our termination condition again. And we repeat that process until our termination condition has been reached. Let's take a look at an example implementation. Here, we are going to be packing our backpack for our hike. We can carry 2.5 kilograms total. We want to maximize the weight limit utilized. This is our constraint. And we want to maximize the value of the items. So this is how much value do we get out of the items that we have packed. So say we have the following list of items. Bottle of water, it weighs 0.7 kilograms and adds 15 points of value. Snacks, a weight of 0.13 kilograms and adds a value of 8. Hat, weight of 0.45 kilograms and a value of 10, and so on. The total weight of the items is about 5 kilograms, which is double what we are able to carry. So we obviously can't take all of the items. We need to figure out which items offer the most value while also fitting into this 2.5 kilogram. Here is an example of one individual. It packs snacks, hat, and umbrella. So a 0 means that the item has not been packed. A 1 means that the item has been packed. And each 0 and 1 corresponds to an item in this list at the same index. So the first one is bottle of water, the second one is snacks, the third one is hat, and so on. This combination has a total weight of 1.95 kilograms. This is less than our constraint of 2.5. And the value of the items is 20. We have another combination here. It has a bottle of water, snacks, sunglasses, and a laptop. The total weight of this combination is 2.267 and has a value of 38. The first thing we need to do is create our list of items. So we're going to come down here. We're going to define what an item is. So create a class called item. The init function will take self, name, weight, and value. We are going to assign these values that have been passed in to our item. Self.name equals name, self.weight equals weight, and self.value equals value. Next, we are going to initialize our list of items. So this will be an empty list. And we are going to append each of these items to our list. So, items.append, create a new item. We will pass in bottle of water, 0.680389 for the weight, and a value of 15. We'll do the same thing for snacks. A weight of 0.136078 and a value of 8. Items.append item happed, a weight of 0.453592 and a value of 10. Items.append item sunglasses with a weight of 0.3175147 and a value of 10. An item camera with a weight of 0.907185 and a value of 9. An item of umbrella with a weight of 1.36078 and 2 for the value. And lastly, an item of laptop with a weight of 1.13398 and a value of 5. Next, we are going to define what an individual in our algorithm is. So we come up here at the end of item, we come and create a class called individual, and the init function will take in self, our list of items, a chromosome, which we will default to an empty array or list, and a generation, and that will default to 0. So this will be the generation that this individual was created in. We are going to assign these values to our individual. So self.items equals items, self.chromosome equals chromosome, self.generation equals generation, and then we are going to create two other attributes. The first one is value, and this will default to negative infinity because there can't be anything smaller than negative infinity, and since we are trying to maximize value, we want it as small as possible at the beginning. The other one will be weight, and this will initialize at 0. Next, we want to randomly generate a chromosome if one has not been passed in. So first we will need to come up here and import random from random. And actually that is my JavaScript speaking. We need to, from random, import random. And we come back down here to our initialization function. And if length of the chromosome equals 0, then we want to randomly generate one. So for blank in range length items, we want to append either a 0 or a 1 to our chromosome. So if random is greater than 0.5, self.chromosome.append 1. Else, self.chromosome.append 0. And that takes care of the initialization function. Next, we need to create our fitness function. So this will tell us how well our individual meets our criteria. So define fitness, takes in self and a weight limit. This will be our constraint. Create two variables initially, a weight and a value. These will hold the sums of our combination. We want to loop over our chromosome. So for I in range length of self.chromosome, if self.chromosome at position I equals 1, that means it has been packed, so we want to add it to our weight and value. So weight plus equals self.items at position I dot weight, and value plus equals self.items I dot value. Next, we want to see if the combination breaks our limit. Then we want to immediately return, give it the smallest possible value that we can, so that it is naturally weeded out. So if weight is greater than weight limit, then we want to set self.value equal to negative infinity and return, because we don't want to waste unnecessary resources on a combination that we already know doesn't work. If at the end of our loop weight is less than or equal to our constraint, then we want to set self.value equals the value that we've accrued, and self.weight equals the weight. And that takes care of our fitness function. Next, we want to define recombination for our individual. So for this example, we're going to use what is called a single point crossover. This takes two individuals, so in this case two different chromosomes, and it splits them at a random point and then recombines them together to make two new individuals. So it'll take, let's say, the first half of individual 1 and combine it with the second half of individual 2, and then it'll do the reverse. It'll take the second half of individual 1 and combine it with the first half of individual 2. So what that looks like in code is define single point crossover, takes in self and an other individual. We want to first generate a cutoff point. This will be the point at which the chromosome is split. So we want to get a whole number. So we want to round the result of random, which is a number between 0 and 1, randomly generated, times the length of our chromosome. Next, we want to build the child chromosomes. This will be other individual dot chromosome from the beginning until our cutoff, plus self dot chromosome from cutoff to the end. And then we do the reverse. Self dot chromosome from the beginning of the list to the cutoff point, plus other individual dot chromosome from the cutoff to the end. Then we create two new individuals from our new chromosomes. So individual self.items child chromosomes 0 and self.generation plus 1. So what this is doing, creating a new individual, we're passing it the list of items, and then we are giving it the first chromosome that we generated here, and we are incrementing the generation by 1. So an individual from generation 1 will have offspring that is in generation 2. And then we do the same thing for our other chromosome. Self.items, child chromosomes 1, and self.generation plus 1. Finally, we return the children. The last function that we need to create on our individual class is a mutation function. This takes in self and a rate, 0.01. It generally stays between 0.01 and 0.05. This will be 1% and 5%. So what this is going to do is it is going to loop through our chromosome, and it is going to take a random number and see if it is less than our rate, and if it is, then it is going to flip the bit at that position. So if the chromosome at position I, if the bit at position I is 0, it is going to change it to a 1. And likewise, if it is a 1, it is going to switch it to a 0. And that covers our individual. Now that we have our individuals and our items defined, let's set up our genetic algorithm. We are going to create another class called GeneticAlgorithm, and the initialization function for this will just take in self, and we'll create a couple attributes to begin. So self.population size, this will be how many individuals are in a population. Self.population, an empty list, this will be the set of individuals. Self.generation, this is the current generation that our algorithm is on. And self.best solution, and this will start out as none because we don't currently have a best solution. So this will be our best solution that we have found thus far, and at the end of the algorithm, this is what will be returned. First, we need to initialize our population. So we are going to create def initialize population. This will take in self, population size, and items. It will store the population size on self, and same thing for the list of items. Then we want to create an individual for the population. So self dot for in range of self dot population size, we want to append a new individual to our population. So append individual, and we are just going to pass it in self.items so that it randomly generates a chromosome and then initializes at generation 0. Next, we are going to call two methods that we will define in a moment. The first one is calculate fitness. And if I can spell it correctly, calculate fitness. And then self.order population. Finally, we will store the current best solution, which in this case will be self.population at position 0, because this method here will order the population from highest value to lowest value. So the first item or individual in the population will be the best fit one. Next, let's define calculate fitness. So def calculate fitness. This will just be a helper function that loops over the population and calls the fitness function on each individual. We will pass in self.weight limit, which we will define later on. And next we will define the order population method. Again, this is a helper function that is simply going to order the list of individuals from greatest value to lowest value. So we use the Python sorted function, takes in the list to sort, the key on which to actually perform the sorting. So we're going to use a lambda function here, lambda individual, and we want to return the individual.value. So this will look like a list of numbers that gets sorted and then is set to the population. Next, we need to define a function that selects the current best individual and updates the self.bestSolution value. So define select best individual. This will take in self, and if self.population 0.value is greater than self.bestSolution.value, then that means that we have a new best solution and we want to store that. So self.bestSolution equals self.population 0. Next, we will create a helper function that sums up the values of our population. So we want to create a sum variable that starts at 0 and loop over each individual in the population. And we are going to increase sum by the individual dot value. And finally, return sum. This will be used for determining which individuals should be carried on from one generation to the next. Next, we're going to create a method that selects parents from a generation. So define select parent, and this will take self and sum value, which will be the return from our method sum values. And we will create an index pointer starting out at -1 and generate a random value that is some portion of the sum of values of our population. So random times sum value, and create two variables, sum and I, that are both initialized at 0. And while I is less than the length of the population and our sum is less than our random value, we want to increase the sum by the self.population at position I dot value, increase the index, and increase I. Finally, we return the index. This will be the index at which the parent is located. Next, we will create a helper function that will allow us to visualize the current generation. So define visualize generation. So we'll take self, and we want to store best in store the best solution in variable best, and we are going to just print out some information about it. So we want to know what the current generation is. Generation self.generation. The total value of the current best solution. So best.value. The total weight of our current best solution. Best.weight. And the chromosome of our current best solution, best.chromosome. This will just give us a more human-friendly, able to read what our population is doing and how it is growing. Next, for the main solution generation, we are going to create a method called solve. This will take in self, a mutation probability. This will be our rate that is used in the individual dot mutation method. Number of generations, so how many generations should this algorithm run for? A population size, how many individuals should be in our population? A weight limit, what is our constraint? And then our list of items. To start off, we will store the weight limit constraint on self. We will then call initialize population. Pass in our population size and our list of items. So we now have our individuals generated and sorted and fitted. Next, we want to loop for as many generations as we have specified. So this will be our termination condition. So for in range number of generations, we want to perform the following. First, we need to get the sum of our population values. So we're going to use self.sum values. And we are going to then create a new population. So we start out with an empty list. We want to loop for the length, half the length of the population. So we want to maintain whatever this population size is that we've specified. If it's 20, we always want to make sure that every generation only has 20 individuals in the population. So if we create 2 children for each individual in the population, then that doubles each time, or each generation that we go through. So in order to prevent that, we do range 0 self.population size. So this will loop for 0 until we reach the population size. And we are going to pass in 2, so it'll go 0, 2, 4, 6, 8, like that. Next, we want to select 2 parents. So parents equals self.select parent, and we want to pass in the sum of our values. And for the second parent, we do the same thing. So this will be these are 2 indices representing an individual in our population. Next, to create our children, we are going to run the single point crossover, or our recombination method, on our parents. So children equals self.population parents 0, and we're going to call single point crossover and pass in self.population parents 1. Next, we need to mutate our children, or give them the opportunity to mutate. So children 0.mutation, and we pass it the mutation probability, and then we do the same thing for the other child. Finally, we need to append our children to the new population. So children 0 and children 1. That takes care of what we're doing in each generation. So that takes care of what we are doing for generating the new population. Next, we are going to store the new population on self.population. We are going to calculate the fitness of our population, order our population from best fit to least fit, and we are going to select the best individual from our current generation. We increment generation by 1, and we print out the best individual in our generation. And that takes care of our generation handling. At the end of our generation loop, we want to visualize what the best individual was overall. So we are going to print out best solution, and we want to visualize the generation in which the best solution was found. So self.bestSolution.generation. the total weight or total value of said best solution value, the total weight of said best solution, and the chromosome of the best solution. And since the chromosome is not as human readable as we would like, we are going to print out a friendly list. So we're going to print out items packed, and we are going to loop through our chromosome for I in range self.bestsolution.chromosome, and we are going to print out the items that were packed. So if the bit at position I is a 1, that means that it was packed. So we want to print items at that same position I dot name. And finally, we return the best solution. Now that we have all of our pieces of our genetic algorithm defined, all we need to do is run it. So we're going to define our mutation probability, and we will set it to 0.01. We want to define our number of generations. Start out with 100. Our population size, start with 20, and our weight limit constraint, and set it to 2.5 kilograms. We need to instantiate our genetic algorithm, and we are going to run our solve method. So result equals ga.solve, and we're going to pass it our mutation probability, our number of generations, our population size, our weight limit, and our list of items. And we actually need to move this down here. And now, if we bring up our terminal with on Windows Control backtick, we can run our Python program. So we're going to type Python backpack.py, and there we go, blazing fast. So you can see here it runs through the generations from 1 to 100, printing out the best solution in that current generation. So in the first generation it was had a value of 44, a weight of 2.35, and this is the chromosome. We go through in generation 8, the total value is now 52, and the total weight is 2.4947587, and this is the chromosome. And this, for this particular problem, this is actually the optimal solution. And you can see that going through it didn't find a better solution. So here it is. Best solution, it was found in generation 8. Total value of 52. Total weight of 2.49. and the chromosome was this. The items that we packed, it looks like we have an error in our code. So if we go up to this part, here's the issue. For range length of self.bestsolution.chromosome. So if we run this again, I'm actually going to clear the console first, and again. So we run this again. Here you can see it performed much worse. So the first generation had no valid solution. So value of negative infinity means that it broke the weight limit. In generation 5, it went up to 14 for value, and the optimal solution that it found had a total value of 32. So this time it did not perform very well, and this is where the if you need an exact solution comes into play, because this will only put out the optimal solution that it happened to find in the constraints that we gave it. So generation 15, total value of 32, total weight, it nearly maximized the weight utilization, but the value is terrible. And these are the items that it packed: snacks, sunglasses, camera, and laptop. If we run it again, you'll see that it's changed again. So total value of 38 found in generation 13, bottle of water, snacks, hat, and laptop. And again, generation 66, total value of 32, snacks, sunglasses, camera, and laptop. So we're going to play around with these and see if we can't get it to perform a little bit better. So I'm going to bump the mutation probability up to 5%. We'll run it again. 61 generations came up with 44. Bottle of water, hat, sunglasses, camera. Run it again. Generation 73, a total value of 42. Run it again. Generation 5, total value of 37. So there was a bit more value in the combinations, but still not great. Let's try increasing the population size. So there will be 200 individuals in each population for each generation. So if we run it, it takes a little bit longer, but generation 42, total value of 37. Generation 18, total value of 37. Generation 38. So it really gets stuck on this one value, which is interesting. Let's try increasing the number of generations. So it'll have more opportunities to get things right. Here, it found in generation 25 the optimal solution of 52 with a weight utilization of 2.4947587, and bottle of water, snacks, hat, sunglasses, camera. Run it again, see if we can recreate it. Generation 9, total value of 52, optimal solution. Run it again. Generation 204, total value of 52. So you can see that by playing around with these different parameters, mutation probability, number of generations, and population size, we can arrive at a more consistent, more optimal solution. The single point crossover recombination method is probably the most basic version of a recombination method. I'm going to show you a few others, namely 2-point crossover, uniform crossover, and the sinusoidal motion crossover. First, I am going to create a helper method that will run these different crossovers multiple times in order to generate a couple averages to see which one in general may perform the best. So we are going to define a new function outside of our classes called solveMany, and this will take in similar parameters to our genetic algorithm solve method. So mutation probability, number of generations, population size, weight limit, our list of items, and then a new parameter called number of iterations. So this will be how many times should we have a genetic algorithm solve our given problem. So we are going to first create our list of recombinations. So this will be single point crossover, 2-point crossover, uniform crossover, and sinusoidal motion crossover. So those are our 4 different recombination methods that we are going to be testing. So we are going to loop over our recombinations. So for recombination in recombinations, we want to store the results of each iteration. So we have an empty list here, and we want to loop for as many iterations as we've defined here up in the number of generations. So for range in number of iterations, and we are going to create a new genetic algorithm, and we are going to append the result, so the best solution from that genetic algorithm. So results.append ga.solve mutation probability, number of generations, population size, weight limit, items, and we are going to pass in the current recombination method being accessed. And then finally, once we have our list of results, we are going to print out some statistics on the results. So we are going to create a new line, recombination method used, and this will be what the recombination value is. We want to see what the best value was. So we are going to utilize the NumPy package. So we'll come back up here to the beginning. We are going to import NumPy as NP. And then we're going to go back down and we will use np.max, and we will pass in a list. It will be i.value, so individual.value for I in results. And I am actually going to store this in a variable. So results values, and I'm going to pass this in instead because we'll use this multiple times. I want to see what the worst value was for our recombination method. So numpy.min results values. I want to see the average total value that our genetic algorithm found. So numpy.mean, and pass in the results values. And next we are going to be printing out information on the weight. So up here I'm going to create another variable that is results weights, i.weight for I in results. Come back down here, and now we're going to print out best weight, numpy.max results weights, the worst weight, numpy.min results weights, the average weight, numpy.mean results weights, and then we are going to print out the average number of generations that it took to generate this best solution that it came up with in each iteration. So average generations, and we will pass it or print out the mean of i.generation for I in results. And that takes care of our solve many function. So down here we'll call it. So we'll pass in mutation probability, number of generations, population size, weight limit, items, and we'll start out with 20 iterations. So it'll run single point crossover 20 times, 2-point crossover 20 times, uniform crossover 20 times, and sinusoidal motion crossover 20 times. Before we can run this, we need to make a few changes to our existing code. So first, let's close our terminal. And we are going to come up into our GeneticAlgorithm class to our solve method, and we are going to have it take in a recombination to use. And we will default it to single point crossover. Next, we need to update our children generation to, instead of always using the single point crossover, we want to have it dynamically utilize whatever recombination method we have passed in. So what we're going to do is remove this remove this piece. We want to wrap the self.population parent 0 in parentheses, and we are going to utilize the getAttr function. So what this does is it dynamically accesses an attribute on this first parameter that you put in. So this is our individual, and we are going to access the recombination method that we've passed in here. So if it is single point crossover, it'll say, hey, get the attribute of this individual that matches this name. And we want to also specify what to do when we have given it a a attribute name that does not exist. So we'll just do a simple lambda function here that prints out recombination function not found. And it still gets called with this, so this will evaluate to single point crossover, and it will call with this parameter, self.population parents 1. Now that we have our genetic algorithm solve method set up to dynamically utilize different recombination methods, let's define our recombination methods. So we'll come up to the individual class, and just below single point crossover, we will define a new method called 2-point crossover. So this one performs in a very similar way to the single point crossover, but instead of generating one random cutoff, we generate two. And then we take 2 parts from one individual and combine it with 1 part of the other individual. So this also takes in other individual. And now for cutoff 1, we are going to generate the same, generate a random number in the same way. So round random times length of self.chromosome. And we are going to initialize cutoff 2 as cutoff 1. So right now what we are doing is we are setting up to ensure that these two are not the same value, so that we're not splitting at the same position. So while cutoff 2 is the same as cutoff 1, we want to generate a new random number. So we are going to set cutoff 2 equal to round random times len self.chromosome. So again, this is to ensure that they are not the same value. Now we want to sort our cutoffs so that we are able to access them in sequential order. So cutoff 1, cutoff 2, and this will merely sort them from lowest to highest. So now we create the child chromosomes in a similar way to the single point crossover. So self.chromosome from 0 to cutoffs 0, and then we add on the other individual chromosome from cutoffs 0 to cutoffs 1. So this will be the middle portion of the chromosome. And finally, we add on the end of the chromosome for self. So from cutoffs 1 to the end. And now we do the same thing, but as the other individual, providing 2 pieces. So other individual, 0 to cutoffs, other individual got chromosome from 0 to cutoffs 0, plus self.chromosome from cutoffs 0 to cutoffs 1, and other individual dot chromosome from cutoffs 1 to the end. lastly, we create our children. This will be the exact same as the single point crossover. So self.items, child chromosomes 0, and self.generation +1. And same thing for the other chromosome. Self.items, children chromosomes 1, and self.generation +1. And return children. Next, let's define our uniform crossover recombination method. So define uniform crossover. This will take self and other individual again. And what this method is going to do is it will loop through the chromosomes and it will interlace them essentially. So it'll be kind of like zipping them together to create two new organisms or individuals. So what that looks like is first we need to create our child chromosomes, and they will just be empty lists to begin with. We will fill them. We want to loop over our chromosomes, so for I in range length of self.chromosome, if I modulo 2 equals 0, so if it's an even number, then we want to append it. We want to append self.chromosome at position I to the first child chromosome and other individual.chromosome to the second chromosome. So child chromosomes 0, so the first one, append self.chromosome I, and then child chromosomes 1 dot append other individual dot chromosome at position I. If it's an even number, then we want to do the reverse. So else child, and actually I'll just copy this. So if it's an odd number, then append self.chromosome position I to the second child, and append other individual at chromosome I to the first child. And finally, we will create the children. That doesn't say children. I will, since it's exactly the same, I will copy from the 2-point crossover and paste it down here. And these are actually, I named it child chromosomes, but it's exactly the same. Individual, pass it self.items, child chromosome first position, increase the generation, and then create the other one for the child chromosomes position 2. And then return the children. Lastly, we are going to create the sinusoidal motion crossover. So what this crossover does is it loops over the chromosomes in sequential order, and it'll take the current bit from self and append that at the first position. Then it will take the first bit from the other individual and append that at the second position. Take the second bit from self and append it to the third position, and so on. And this way it creates two offset chromosomes. So in practice, this is what this looks like. Define sinusoidal motion crossover. We pass it self and other individual again. We want to define our child chromosomes, and these will be two empty lists again. For I in range length of self.chromosome, we want to, if the first chromosome is not at the max length, so the length of the items, then we want to append to it. If it is at max length, then we want to append to the second item, or second child chromosome. So if length of child chromosomes at position 0 is less than length of self.chromosome, then we want to append to it child chromosome 0.append self.chromosome at position I. Else, we want to append to the other one, to the second child. So self.chromosome at position I. And we are going to do the same exact thing for the other individual. So if len child chromosomes at position 0 is not full yet, self.chromosome, then we want to append the other individual chromosome at position I. Chromosome at position I. Else, append it to the second child. Dot append other individual dot chromosome at position I. Finally, we are going to create the children and return them. So I'll just copy from the uniform crossover and we are good to go. Now let's see how our different crossovers perform. So we'll come down back to our solve many function, and before we run this, we want to prevent the previous genetic algorithm solve function from running. So we'll just comment it out, and so now it should just run the solve many, and it'll loop through, it'll do our different recombinations, and let's see how they perform. So we'll come into our terminal, we'll clear it out, and then we will run the backpack.py file again. Here we are. I'm actually going to cancel that and come up here to our genetic algorithm solve function and comment out the visualize generation piece and the best solution piece, as well as the items packed. So that should clean up the console a bit. So we'll come back into our terminal, clear, and we'll run this again. And you can see, since we have our number of generations set to 1000, it takes a little bit to run for each one. But here we have our 4 solutions. So, single point crossover, it had a perfect solution in every single generation, and it took an average of, or it had a perfect solution every single time that it ran, so for every iteration, and it took an average of 67 generations to find the optimal solution. 2-point crossover, same thing, but it found the optimal solution in an average of 107 generations. And uniform crossover had the same optimal solution and took 59 generations on average to find it. You can see that the sinusoidal motion crossover here, it actually performed far worse than the other three. The other three were very similar, but this one found a optimal solution of 28, which is not very good. And it took an average of 146 generations to achieve this. So let's run this again and see if they perform any differently. So we have the single point crossover. Again, it found the optimal solution in 232 generations on average. 2-point crossover performed a bit worse. It didn't find the optimal solution every time, but it did find it sometimes. It looks like it may only have failed to find the optimal solution once, and it took an average of 236 generations to find its optimal solution. Uniform crossover, it looks like, performed the same as the 2-point crossover, but it took an average of 265 generations to find. So these three perform very similarly. And then again, the sinusoidal motion crossover could only find a best value of 28, and average generations was 130. So as you can see here, there are different recombination methods that you can try. Some might meet your needs, but some may not. So sinusoidal might not be the best when your chromosome lines up with a set order of items. It might perform better in a scenario in which you just have your chromosome is just a list of numbers and you need to find the correct combination of them, but they don't necessarily, their position doesn't necessarily correlate to an item list. So all that to say is do your homework, figure out what methods have what benefits, and if that meets what your problem needs. So thank you for watching, and good luck in implementing your own genetic algorithm.